Welcome to the course on computer design of electrical machine. So we'll have a lecture 24 today on design of synchronous reluctance machine part 2. So the outline of presentation is the design of synchronous reluctance motor, then power drive motor design, then design methodology by case study, then PM assisted reluctance motor considering saturation effect and PM assisted line start motor design, then numerical question with the numerical references. So coming to design of synchronous reluctance motor. So well, the power drive motor design aspect in the power range of tens to hundreds of kilowatt, the limitations of power electronics, voltage current ratings and the cost becomes very important and determine the torque speed attainable NLF. So in general, only continuous torque speed NLF is imposed and this comprises a constant torque zone followed by a constant power zone from WB up to maximum speed as shown in the diagram. Up to the base speed, a constant DQ current control may be applied, and as the DQ current constant angle implies a proportional decrease of ID and IQ, so such control may not provide a constant power over a wide range. So as continuous torque is to develop over the entire speed range, the copper and coal losses should be kept in as small as possible, while the power factor should be high to reduce the kVA input to the motor. So thus it seems the maximum power factor DQ current control, that is ID upon IQ equal to under root LQ upon LD, should be applied up to the base speed. Hence, a considerable torque reserve for the constant power zone at the price of some inevitable decrease in the power factor. So control law for the constant power zone results from the constraints lambda is under root LD ID square plus LQ IQ square, that is approximately equal to Vs upon omega r, for omega r equal to greater than omega b, and T equal to Tm omega b upon omega r, that is 3 by 2 P1 LD minus LQ ID IQ. So in order to increase the torque speed and NLF, it is preferable to use the maximum torque for a given flux control stage, that is constant current control angle, that is ID upon IQ equal to LD upon LQ, LQ upon LD. So with IDK per phase will be VR phase divided by omega r LD under root 2 for omega r equal greater than omega b, and maximum speed omega r next for constant power is computed T equal to Tm omega b upon omega r equal to 3 by 2 P1 in bracket LD minus LQ into IDM square per phase LD upon LQ, and this results in T equal to Tm omega b upon omega r 3 by 2 P1 LD minus LQ IDM square LD upon LQ, and your omega r max upon omega b will be equal to VR phase divided by omega b square into 3P1 LD minus LQ upon 2 LD LQ into Tm. So smaller is the Tm, the higher is the maximum speed at constant power, AP equal to Tm omega b upon P1, and the DQ current angle gamma between omega b and omega r vary as gamma m equal to tan inverse under root LD upon LQ to your gamma k equal to tan inverse LD upon LQ. As you can see, vector diagram for peak torque and omega b equal to omega rb maximum. So coming to power drive design aspect, so initial data, the power SRM drive design is taken as an example. So torque up to the base speed Tm equal to 100 Newton meter, base speed 1200 RPM, that is 40 pi radian per second, and number of poles pair is P1 equal to 2 or 4 pole, and DC input to the PWM inverter is V equal to 800 V, and the constant power up to maximum speed to 2400 equal to omega r max 80 pi radian per second. So now coming to rotor diameter dr and the stack length L. So design begins with the torque Tm expression. So Tm equal to 3 by 2 P1 LD minus LQ into IDM star and IQM star, where IDM star upon IQM star equal to under root LD upon LQ upon LD, and the torque Tm at base speed omega b corresponding to the rated phase voltage, that is VR per phase. So VR per phase equal to root 2 V 0 upon pi into kV 0, where kV 0 varies from 0.9 to 1. So now the rotor diameter dr and the stack length L, the air gap density BD1 and BQM are given as BD1 dm square plus B1 QM square equal to B1, G maximum equal to 0.73 0.74 Tesla. So with the with B1 QM equal to B1 DM KQM 1 upon KDM 1 under root LD upon LQ. And typically the ratio T upon tau upon G is assigned 300 and KDM and QM are obtained from the figure. So KDM 1 equal to around 0.97 and KQ1 equal to KDM 1 upon by 28. So here you can see the variation how these KDM1 and KQM varies with the pole pitch. Now, since the leakage inductance L sigma S sigma is not known, it is assumed that L sigma equal to LQM and thus LD upon LQ equal to LDM plus L sigma M divided by LQM plus L sigma KDM 1 plus KQM 1 divided by 2 KQM 1 equal to KDM 1 upon 2 KQM 1 plus half, that is putting value 28 by 2 plus 1 by 2, that is 14.5, and B1 DM is calculated from B1 DM equal to 1 BGM 1 maximum under root 1 plus KQM square upon KDM square into LD upon LQ, or putting a value it comes 0.72334 Tesla. So now the Carter and saturation coefficient are assumed, the value Kc equal to 1.2 and Ks equal to 0.35. So taking L upon tau equal to 1.6 and tau upon G equal to 300, the pole which is calculated from the relation tau equal to cube root of TM KDM 1 square mu 0 tau upon G into tau upon L divided by BD1 square P1 square KDM 1 minus KQM under root LD upon LQ into Kc in bracket K plus 1S, and putting value it comes 0.1208 meter, and the stack length L equal to tau into L upon tau, so that comes around 0.19328 meter, and the air gap G can be determined from equal to tau upon G upon tau, it comes around 0.4 into 10 power minus 3 meter, and the rotor diameter is dr equal to 2 P1 tau upon pi, that comes 0.15388 meter. The rotor has 4 poles for this condition, and the pole 2 upon pole pitch is tau P upon T equal to 2 by 3. So SRM rotor poles are made with axial laminated 0.35 mm thickness laminations, and BTR equal to 0.35 mm interleaved with the insulation of layer 0.21 mm thickness. So BSR equal to 0.21, as you can see in the diagram with the structure of design synchronous reluctance motor. So now coming to design methodology by case history, let us design a MFBA rotor 2-pole 3-phase reluctance synchronous motor that whenever inverter fed is at 380 volt DC produces Pn equal to 1.5 kilowatt and a maximum speed of 4500 rpm for a efficiency above 90%. So no constant power speed range. So CPR ratio is necessary typically for air compressor kind of load. So for an estimated efficiency eta equal to 90%, the rated electromagnetic torque is equal to Tn equal to Pn upon n 2 pi and theta and max, and putting a value to come 3.538 Newton meter. Adopting a specific shear stress on the rotor Ft equal to 0.7 Newton meter centimeter square and interior stud diameter and DIS equal to 60 millimeter. The stator core length L is obtained at Tm equal to F1 DIS L DIS by 2. L comes, putting a value from there, it comes 0.1, that is 100 millimeter. And this is the tentative rotor configuration as shown in the figure with the typical winding and the rotor configuration. So typically 2-pole MFBA rotor of reluctance synchronous motor with 15 stator slots and 20 equivalent rotor slots with flux barrier. So aspect ratio of stator is given by L upon tau equal to 100 divided by pi dr by 2 nr, and putting value it comes 1.05, which is rather favorable for shorter per unit coils and connections. And while the D-axis field distribution and inductance LDM are straightforward, for Q-axis there are two main flux inductance components. One flux that goes through the rotor segments and across the flux barrier LQMF, a circulating component across the air gap due to the shaded area, and variation that is LQMC, and apparently the ratio LMQC on LDM decreases with the increased number of the rotor flux barrier, so such that the for 4 segments per pole the ratio of LQMC upon LDM equal to 0.027. So the thickness Lk of a flux barrier is proportional to the square root of the its depth per half pole pitch Sk, with the Sk decreasing towards the Q axis. So will be Lk. Thus for the 4-pole total LQM F divided by LDM equal to 0.04. So now the rotor flux bridges, that is ribs, introduce an additional component of for the Q axis magnetization inductance LQ M ribs, which diminishes both average and power factor. So LQM ribs equal to 4 upon root 3 L N1 KW1 upon IQ into BS, where BS is the flux density in the rotor flux bridges, varies with the IQ hysteretic current in quadrature axis. Thus, the total magnetizing induction LQM equal to LQMF plus LQMC plus LQM ribs. So, thus expression of LDM equal to LM into KDM. So, taking LQM ribs upon LM equal to 0.025, so LQMF upon LM equal to 0.23 and LQMC upon LM equal to 0.03 and LDM equal to 0.95 into LM. So, for 60% iron and 40% air proportion in the rotor core, finally LDM upon LQM, putting the value, it comes 12 by 1. So, if LS1 equal to 0.05 LDM leakage inductance, then LD upon LQ, that is LDM plus LS1 divided by LQM plus LS1, that comes around 7. So, magnetic saturation will be kept low, especially in the rotor, to preserve this total saliency under the full load. Also, the hopefully LS1 will be smaller than above when calculated. So, current ID provides machine magnetization, and for an 18 slot 2-pole stator, 2-layer sorted coils winding with the KW1 equal to 0.925. The slot MF along with B axis for magnetization RMS is NDID RMS equal to B1 GDMS pi GKC1 in bracket 1 plus KS divided by 302 mu0 Q KW1 KDM, putting a value, it comes 80 ampere turns per slot. So, BG1D, the peak air gap no load flux density in the air gap is chosen B1DM equal to 0.7 Tesla. And the machine for maximum power factor, for which ideally IQ equal to ID under root LD upon LQ. So, for this case, the ampere turns per slot RMS will be NSIS equal to NSID square plus NSIQ square, and putting a value, it comes 215 ampere turns per slot. Now, LM equal to 6 mu0 T tau L UNS KW square divided by pi square UKC in bracket 1 plus KS. So, it comes 0.09 NSA square into 10 power minus 3, and here LDM equal to LM KDM1 LM KDM1 KQM1 or LD equal to LDM plus LS1 plus LQ equal to LQM plus LS1. So, torque expression here is Tm equal to 3P1 LD minus LQ into RD phase into IQ phase, and putting value, it comes 3.7 Newton, which is greater than 3.5 Newton. So, the machine produces the required torque with the result. So, maximum power factor cos phi maximum is equal to 1 minus LD upon LQ upon LD divided by 1 plus LQ upon LD. So, putting a value, it comes 0.75. So, it could be 0.77 when losses are considered. So, stator slot geometry is determined easily when we know the slot MF NSI is equal to 15 ampere turns per slot, and assuming current density J equal to 4.77 ampere per millimeter, the slot fill factor carefully 0.45. So, slot useful area is equal to A slot NSIS divided by J K fill, and putting value, it comes 100 millimeter square. So, since the slot pitch for an 18 slot 2-pole tau is equal to tau upon 9, that is 10.46 millimeter. So, for tooth width of 5 millimeter, the slot width is 5.46 millimeter. So, with the slot depth HS 13 millimeter, the recalculated area for typical slot is A slot equal to WS1 plus WS2 by 2 into HSA, and putting value, it comes 103.906 millimeter, which is greater than 100 millimeter square. These are the typical the shape how the slots are there with the different dimensions, with the slot geometry. So, now coming to stator yoke, SCS equal to SCS upon tau upon pi into BG1 max upon BCS max, and putting value, it comes 15 mm, and leakage inductance LS1 can be computed from LS1 equal to 2 pi 0 NSPQ square upon PQ into L in bracket lambda S plus lambda Z plus lambda F, and where lambda S equal to 2 HSA upon 3 WS1 plus WS2 plus HO-S0 divided by WS0 plus W2H upon WS1 plus WS1. Putting a value, it comes 1.095. The air gap leakage coefficient lambda equal to lambda Z equal to 5G upon the 5WS plus 4G, and it, after putting value, it comes 0.15. So end connection length of the stator winding LF equal to pi into top by 2 is computed considering the end coil as a semicircle with a average diameter equal to the coil average opening. So lambda F equal to 0.34 Q upon L in bracket LF minus 0.64 tau, that is 0.59. So leakage inductance results in LS1 equal to 2 mu 0 NS PQ square upon PQ into L in bracket multiplied in bracket lambda S plus lambda Z plus lambda F, and putting value, it comes 1.382 10 power minus 6 NSC square. So the phase resistance RS equal to rho 120 LC P1Q NSC square J con upon NSIM, and that is equal to 0.068 NSC square 10 to power minus 2 at 100 degree with the PCO equal to 0.3 10 to power minus 8 ohm meter 400 degree Celsius, and extrude length LC equal to 2 in L plus LF equal to 444 millimeter. Now to calculate the number of turns per slot, and that satisfy the limits of AC phase voltage Vs equal to 152 volt for 380 volt VDC. So LQ equal to 11.8 into 10 power minus 6 10 minus 6. So NSC square into NSC square already equal to 91.6 into 10 power minus 6 NSC square. So RS equal to 6.8 into 10 minus 4 and then into NSC square. So NSID equal to 80 ampere turns, NSIQ equal to 200 ampere turns. So DQ, what is the equation? VD equal to minus omega R LD LQ plus RSID, that comes 0.98 NS, and VQ equal to omega R ID LD LDID plus RSIQ, that is 3.5578 NS VD. So NS equal to, from these two equations, 1 to under root 0.98 square plus 3.5578 square, so it comes 42 turns per slot. As the winding had two layers, so each coil have 21 conductors. So conductor diameter DCO equal to under root 4 upon pi ACO, where ACO is IM upon J con, and or NS IM upon NS J con equal to, putting a value, 215 by 42 into 4.77. So DCO comes 1.1 millimeter. So power factor now cos phi equal to P upon 3 PS IM into eta. So putting the value, it comes 0.705, and this value is lower than the initial approximately calculated one, leaving room for improvement in the design or adopted for the design safety. Now coming to the typically design of PM assisted reluctance motor. So synchronous reluctance machine suffers a drawback like low power factor and the torqueable. Figure A shows the two four pole reluctance motors characterized by 2 and 3 phase flux barriers per pole respectively, and the permanent can be inserted in each rotor flux barrier as in figure B, with so the two motors characterized by 2 to 3 flux barriers per pole respectively. So here is the sketch of synchronous reluctance motor and the PM assisted synchronous reluctance motor with 2 flux and 3 flux barrier pole, and synchronous reluctance motor and B is the PM assisted synchronous motor. How the permanent are put in the flux barriers into kind of type of synchronous reluctance motor. And here you can see how the flux linkage varies with the current characteristic highest possible flux density. So reported for synchronous reluctance motor and for PM assisted synchronous reluctance motor. So you can clearly see the effect of the PM as well as the saturation in the two cases like. And now you can see the effect typically on the torque current angle characteristic of the two cases of synchronous and PM reluctance motors like. And then you can say flux line of the and flux density map of synchronous PM synchronous system. So now coming to with the assumptions of a lossless non-hysteresis magnetic motor, the expression of electromagnetic torque is Tm equal to 3 by 2 P in bracket lambda diq minus lambda qid minus delta mc as a function of I diq theta upon delta theta qf, or Tm equal to Tq minus delta mc wmc in bracket m as a function of I diq theta m upon delta m, where P is the number of pole pairs and omega mc is the magnetic energy expressed as a function of rotor position, and theta m is the stator current position and stator current I diq. and you can see now torque behavior typically with the rotor position and with the mechanical, how really in the two cases like PM assisted and your without and with this. So you can clearly see there is an increase in torque produced because of PM. I mean, even with the maintaining the same cell length. So for a given couple of currents, IDIQ, it is possible to split the electromagnetic torque into two components as a permanent torque TPM and a reluctance torque component, and they are given by TPM equal to half in bracket tau EM as a function of IDIQ plus TEM as a function of ID minus IQ, and T reluctance as a function of half TM as a function of IDIQ minus TM as a function of T ID and minus IQ. Now coming to saturation effect, the investigation of the impact of iron saturation on the machine performance carried out, varying the thickness of flux barriers. So referring to the figure, the coefficient Kr is defined as Kr equal to L air divided by L air plus LFE, and that is equal to summation of I as a TBI divided by dr minus dsh by 2. So where the terms TBI, the thickness of flux barrier, dr is the external rotor diameter, and dsh is the shaft diameter. So coefficient Kr has to be chosen according to the stator geometry, that is tooth width and back iron height. Like you can clearly see synchronous machine geometry and variable parameters, I mean typically with the of the different parts. Like so now coming to coefficient Kr related to the stator geometry as follows: Kr s equal to Ps minus Wt divided by Ps. Ps is the stator slot pitch defined as Ps equal to pi ds upon Qs. Wt is the stator tooth width, and it is evident that the rotor Kr should be close to the stator Krs so as to get the machine equally saturated. So you can clearly see with the machine layout Kr equal to 0 to multiply 0 to 35, or with the ratio Kr equal to 0 to 65 configuration. So stator Kr s equal to 0.46, the rotor coefficient has to be selected to Kr equal to 0.35 and typical Kr equal to 0.65 respectively, resulting the typical two geometry. Like so now to determine the convenience of having a Kr equal to greater than Ksr or Kr equal to less than Ksr, two extreme cases are considered. The rotors are designed with the different angles of flux barrier, and that is the north pole flux barrier are slightly different from those in the south pole, so as to minimize the torque ripple. So the optimization can be achieved on the basis of an analytical model or adopting a finite element model of the motor. So this typically results carried out by means of finite elements highlighting the difference in terms of flux, torque ripple, average torque and power, and flux linkage losses and power factor. So increasing the saturation level, that is increasing Kr, the flux density in the rotor increases. On the other hand, in the stator the flux density decreases. The main impact of Kr is the decrease of d-axis flux linkage due to iron saturation. With the higher Kr, that is with the larger flux barrier thickness, the d-axis flux linkage decreases at higher current due to the iron saturation, about the 3 times to decrease in a q-axis flux linkage. You can see the impact of saturation factor for Ks equal to 0.35 or Ks equal to 0.65. So configuration, and on the d-axis and q-axis how really they are decreasing to cases. Now the figure shows the motor torque and power versus speed of the two synchronous reluctance motor, and the torque and the power decrease as the Kr increases, and due to the saturation the MPTA actually changes if the Kr increases from 0.35 to 0.65. Now PM systems, there are several advantages with PM are inserted within the rotor flux barrier, and figure shows the step of the rotor assembling the PM is going into inserted in the rotor flux barrier, as you can see in the photograph as well as in the typically. So inserting a of the assisting power magnets in the synchronous motor rotor flux barrier, and here is the part of PM flux goes into the iron bridge. So now coming to part of the PM flux stands to saturate the iron bridges of the rotor, and such a situation implies a beneficial reduction in the LQ. So moreover, the PM added along with the negative Q axis compensate the negative flux LQ-IQ, and the effect of the PM flux linkage is to rotate the flux linkage vector out of the phase with the respect to the current vector. and since the voltage vector is rotated towards the current vector, the power factor increases. Like so, here you can see clearly the vector diagram of the typically in PM assisted the power factor really get improved, like with because of the PM assisted. Created here the typically the voltage corresponds to sigma m. So PM assisted reluctance motor require a lower volt ampere rating for a given nominal mechanical power, and the electromagnetic torque of the PM motor increases because of a PM torque term is added to the reluctance torque term. And figure next slide shows the air gap flux density distribution together with the fundamental waveform due to the PM magnet in the rotor. And in order to maintain the intrinsic fault tolerance capability of the reluctance machine, the added PM is minimum, and then the back EMF is low. The short circuit current is also low, as well as the corresponding braking torque. So PM flux is quite low, especially when the ferrite magnets are adopted. And you can clearly see how the air gap flux density distribution, the fundamental harmonics is also reported, and the fundamental is quite flux density is quite low in a PM assisted synchronous motor. So now this figure compares the torque and power behaviors of synchronous motor and ferrite assisted synchronous motor. These behaviors have been obtained following the maximum torque per ampere MTPA trajectory, field weakening, FW region 1 constant current and constant voltage, as well as the field weakening region 2 decreasing the current constant voltage, also called the MTPV trajectory. The vertical dashed line separate operating your FW regions 1 and 2, and it is worth noting the PM assisted synchronous motor does not reach the FW region second in the considered speed range. You can clearly see how the MTPA, with the PM assisted reluctance motor virtually torque increases, and really how it is typically the power increase with the because of magnetic excitation. Power produced by the machines it increases substantially. As you can see, at different speed, typically, this is around 6000 RPM. You get almost 3 times the increase in the power because of this PM assisted in this figure. Next shows the another important effect of the adding PM, and that is the increase in the power factor in the whole operating region. The power factor is always above 0.8 and now always higher than the synchronous reluctance motor. So power factor improvement due to the PM is more beneficial as the speed increases. It means that the size of the converter could be lower for the same base torque adopting the PM assisted synchronous reluctance motor solution. Also, the efficiency of the PM assisted reluctance is to be higher than that of synchronous reluctance motor. And you can clearly see the power factor how it is increased. Probably in case of synchronous motor at a speed of 6000 RPM, power factor is below 0.6. However, it is in case of PM assisted synchronous, it's more than, it may be 0.98 order of that, and efficiency certainly there is improvement in efficiency reasonably in lower speed range. So coming to the another example with the line start motor design. So line start reluctance motor require a kind of rotor cage for starting and for damping random oscillations around the synchronous. And on the other hand, typical design approach to synchronous motors is applied in general, considering the absence of field winding and the configuration of the rotor, which results in different methodology for computing the magnetizing inductance and the phase parameters. Line start three-phase synchronous reluctance rotor are built with the magnetically anisotropic rotor, that is LDM greater than LQM, cost of cage winding, and sometimes of PM assisted for better steady state synchronous and efficiency and power factor. So they are proposed to replace induction motor in line start constant speed application in the hope that they can produce higher class of efficiency in economic condition or initial cost and energy consumption reduction for a given mechanical work, leading to an investment payback time of less than 3 years in general. And cage synchronous reluctance motor are applied either as a line start constant frequency and voltage motors or as a generator in general 3-phase devices, but occasionally as a split phase capacitor device. So for the axially laminated anisotropic rotor, only LDM undergoes magnetic saturation. So as the synchronous performance of line start advanced reluctance motors approximately match with the performance of their induction motor counterpart, the output coefficient, electrical loading, air gap flux density, aside initial efficiency and power factor, the air gap rotor diameter relations should be taken in from induction machine design and fabrication experience. You can see the IC60, IC 60,430. Standard include the minimum efficiency requirement of I1, 2, 3, 4 and 5 efficiency classes of common performance according to the given figures. As you can see in the figure how for different standards for 50 Hz and 60 Hz, and the demanding requirement have to put the existing LED and trends in electric machinery R&D and fabrication face to face to assess the potential of meeting them. And this is the line start motor design efficiency potential for various electric motors. And you can see 3-phase squirrel cage induction motor. Then you can see a 3-phase wound rotor and single-phase squirrel cage induction and synchronous motor with PM wound rotor and line start, palm grenade and sinusoidal synchronous motor. And this is a comparison with according to the standard. And this is the performance of your 7.5 kW 4-pole induction motor and line start, palm grenade synchronous motor in in energy efficiency improved to second 3-4. So while the efficiency increases from 87 to 93%, the initial cost of line start palm grenade synchronous machine class I4 is to 33% of that of induction motor of class I. Line start electronic motor with a strong magnetic saliency and eventually with lower cost PM assisted is economically feasible while also providing lower starting current. And you can clearly see line start electronic motor topology with the 2p equal to 2 means typically the 4-pole geometry, and typically line start electronic motor with the topology of 2p equal to 4-pole. So typically finite element derived flux linkage in a synchronous electronic motor with no permanent and ALA rotor and a air gap flux density variation with the rotor position of a given MR in axis of P and Q, and reveal the complexity of the problem and air gap flux density have reached space harmonic content. As you can see how the air gap flux density is with the angular position in the two cases with the of D axis and Q axis. So now it is evident that due to the stator slotting, the rotor multi-flux barriers in the rotor, the air gap flux density in both the D and Q axis shows high efficiency space harmony. Also in the Q axis, the per half a pole, the air gap flux density changes polarity every time, indicating that the magnetic potential of the rotor is not constant. Thus, the flux lines cross the air gap field time, then the stator slot opening, and this is good as the fundamental flux density Pg1 is reduced, but the space harmonics may induce notable eddy currents in the rotor axle lamination. They may be reduced by thin radial slot 3 to 4 per total stack length. And you can just see how the contrary in the regulation lamination multiplex flux barrier, the rotor Q axis air gap flux density is not in the general, so the negative component under a pole, but it's fundamentally reduced less, so the is still notably shown here. As you can see here, flux density versus rotor position, D axis and Q axis, typical for multiple flux barrier. And on the right side with the B, it is PMS produced air gap flux density in synchronous flux barrier rotor. On the top of that, the PM air gap flux density distribution at 0 stator current, and B is with the space harmonics that will become time down harmonics in back EMF. So for a preliminary design or performance calculation, simplified circuit constant parameter formula are required. So for that, only the fundamental air gap flux density is considered at a very preliminary stage. The expression for magnetizing inductance LDM LQ of a synchronous electronic motor with distributed AC winding R. So LDQM equal to 6 mu 0 tau L N1 KW1 square divided by pi square P1 GDQ in bracket 1 plus KSCQ, where D equal to G into KC1 into KC2 and GQ equal to GD1 plus GVB, where N1 is the turn per phase, one current path only, KW1 fundamental winding factor, tau is the pole pitch, L is the stack length, P1 is pole pair, KC1, KC2 Carter coefficient for stator and rotor, and KSQ is the equivalent saturation coefficient, and GFB is the equivalent additional air gap provided by the rotor flux barrier. So average length of flux barriers along with the Q axis flux line, the rotor makes a maximum of 2 into GFB. So magnetic saturation is a complex phenomenon with the local variations, and approximately may be considered dependent on the IDIQ, stator current, and the PMS flux linkage IPM according to the concept of cross coupling saturation. And in the flux barrier rotor at very low current, before the rotor flux bridges saturate, LQM is a large, almost equal to LDL, and as the stator current increase, the rotor flux bridges saturate and the LQM decreases dramatically to produce the reasonable torque by magnetic saliency. So for line start reluctance synchronous motor, this variation LQM to the current is beneficial for synchronous motor self synchronization. And this typically the line start motor design. For the simplification of two pole rotor, the ratio of LDM LQM equal to GQ upon G D with the approximation. So considering the magnetic reluctance in the axis of D and Q, so GQ upon GD equal to approximately G plus GFB plus G gauge divided by G plus G gauge, where GFB is the radial thickness of the flux barrier, only one flux barrier here, and say equal to 9 into G plus G gauge is the equivalent radial gap in the rotor cage bar region, the equivalent height of the rotor cage for infinite core permeability, that is H cage equal to 11 into G, and considering the 60% core and 40% of slot, G is equal to H cage equal to 0.6, that is 6.6 millimeter. So GQ upon GD equal to LDM upon LQM, and putting value it comes 2.18. And this magnetic saliency ratio seems modest, but the higher energy permanent, it leads to outcrystalline performance. So stator leakage inductance LS1, so this component is H4 induction machine, LS1 equal to 2 μ0 W1 square from PGQ in bracket lambda slot plus lambda Z plus lambda N plus lambda diff. And typically here the how the typical stator semi-closed slots, I mean where the winding is put in stator. So from here for here the lambda slot equal to HSU upon 3B SV plus HSO upon 3BSV less than 1.5 to 2, and BS average equal to BS1 plus BS0 by 2, and BS average equal to BS1 BS2 by 2, and lambda Z equal to 5G Kc divided by BS0 into 3 beta Y plus 1 by 4 divided by 5 plus 4 K G Kc divided by BS0, that is less than 0.4 to 0.5, and Kc equal to Kc1 Kc2, the lambda and equal to 0.34 Kg upon L stack in bracket L and minus 0.64 tau, this will be less than 0.7 to 0.8 for double layer winding, and lambda difference equal to 3G upon pi square GKc, and V equal to 1 greater than 1, that is Kw by V square upon V square. So difference leakage inductance component by lambda difference refers to the space harmonics of the stator air gap flux and implies that all these harmonics cross the air gap, and this is true for higher order harmonics if top on pi V greater than G. In the similar manner, MF in Q axis may be written as EMF Q equal to omega 1 in bracket Pg1 Pm into 2 pi upon pi into tau into L flat multiplied W1 Kw1, and Bg Pm1 equal to 4 upon pi Bgm into sin alpha Pm into 2 by pi, and Bg Pm finally equal to Br G Fpm divided by mu recoil divided by bracket GFB upon mu recoil plus G gauge multiplied 1 plus Kf ring E, where all the parameters are given the other function here. So considering the symmetric cage, the presence of the flux bridges below the rotor slots notably reduces the slot leakage permeance lambda slot, and for the simplified rotor slot, lambda slot R equal to HR0 upon BR0 in bracket 1 minus CW square plus HSR upon 3BR bracket 1 plus 3 CW multiplied CW minus 1 in bracket, and CW equal to HR upon BRO plus HSR upon 2 BSR divided by mu RI WI upon BSR plus HR 0 upon BR0 plus HSR upon 2 BSR SN1, where mu RI is the relative permeability 10 to 20 per inch of the flux linkage with WI below the slot, and where WI equal to infinity and C0 equal to 0, and lambda slot gets the standard formula lambda slot are equal to HSR upon BR0 plus HSR upon 3 BSR. And typically you can see the dimensions here, how rotor slot and flux barrier and ending dimensions. So end connections cage ring permeance lambda ring equal to lambda ring equal to 3 E ring upon 3 D ring upon 2 NR L stack sin pi D pi upon PNR into logarithmic 4.7 into D ring A plus 2B should be less than 0.7 to 1. So combined cage bar and its end ring resistances are approximated RB equal to IR bar plus R ring upon 2 into sin square upon pi R P upon NR. And similarly, the bar plus ring section leakage inductance is LB equal to mu0 L stack in bracket lambda slot R plus lambda SR plus lambda ring and the reduced values of RR and R resistor core RR equal to RB into NR upon 3 KI square and LR equal to LB into 3 NR upon 3 KI square and KI, where KI equal to NR upon 6 W1 to KW1. So here typically we can say line start power source line to start page home. Typically residential appliances traditionally make use of the local AC one phase power of the standardized 120 or 220 and frequency of 50 or 60 Hz. So additionally traditional most home appliances, refrigerator, compressor, washing machine, home heater, water pump, ventilator use line start phase rotor induction motor, right? Here you can see how the line start single phase AC 2 pole typical induction motor and then induction motor, and B strong PM reluctance motor and weak PM assisted reluctance motor. And here you can see how the one phase capacitor assisted synchronous reluctance motor, and typically here the cross section of the motor, and typically the flux density and is distribution in their cap. Now coming to the numerical questions. So example, with the numerical one, calculate the number of turns per slot NS for V half page 152. Let the LQ equal to 11.8 10 power minus 6 NS square and LD equal to 9.18 into 10 power minus 6 NS square. RS equal to 6.8 into n minus 4 NS square and DID equal to 80 ampere turns and NS IQ equal to 200 ampere. So since VD equal to minus omega R LQ IQ plus RS ID, that is 0.98 into NS V, and VQ equal to omega R LD ID plus RS IQ equal to 3.5578 NS V. So VR phase equal to VDM square VQM square. So NS equal to 152.98 square 42 turns per slot. And numerical 2, calculate the current angle for maximum torque when ratio of LD and LQ is 10. So DQ angle for maximum 10 theta equal to LD upon LQ 1 upon 10.1, or and theta from here it comes 5.71 degree. Now coming to numerical 3, calculate the current angle of maximum power factor when the ratio of LD is 10. So here DQ current angle for maximum torque condition 10 theta and root L upon LD, and that's 1 upon 10, so equal to 0.36, so theta comes 17.53 degree. Now coming to numerical problem 4, consider PM assisted 3-phase delta connected synchronous reluctance motor with 2 poles, is rectangular rotor bar and other equation given as a line start. VL equal to 380 volt RMS and frequency F1 and 50 Hz, and unit stator diameter DIS equal to 90 mm, stator pole length L stack 90 mm, air gap length equal to 0.55 mm, slot per pole per phase equal to Q equal to 5, rotor slot NR equal to 22 with the elect power of 5 kW at 3000 rpm, PM radius thickness HPM equal to 3 mm, flux barrier FPM radial thickness GFB equal to FPM plus 0.5 at 3.5 mm, flux bridge thickness below slot WI equal to 2 mm, and target type cage or ID cage S40 and cage bar height HR equal to 6 mm, cage bar width equal to BSR equal to 5 mm, rotor slot opening BR0 1 mm, height of the rotor tip HR 1 mm, cross section radial HR plus HSR plus WI 8 mm, and B axial 25 mm, ring average diameter D ring equal to PI is equal to minus 2G minus A, that is 80.9 mm, and remnant flux density BR equal to 1.15 Tesla. PM recoil relative permeability means recoil 1.07, and chordate coils y upon tau equal to 13 by 15, and phase connection delta, and PM is span 135 degree, that is lambda PM. Now coming to the solution, calculate the number of stator turns if no load phase line voltage PM EMF is 0.9 VL RMS, and B all circuit parameter consider the permeability of iron finite and all throughout except the rotor bridges below the slot, that is where the mu RI equal to 10 per minute. Now coming to solution, EPM phase equal to 0.9 PA, that is 342 volt, and 5 PM equal to PM under root 2 pi equal to 1.5395 Weber, AW1 sin pi by 6 divided by Q sin pi upon 6 Q, that is 0.9567, KW2 sin y tau upon pi by 2, that's 0.9781, and KW equal to K1 into KW2 equal to 0.9358. Now BG equal to BR upon FPM upon mu recoil divided by HPM for mu recoil G plus GFB minus HPM into K suffering plus G, that comes 0.6597, where K ring is approximated as K ring equal to 1 pi 1 plus 2 WI mu mu RB divided by lambda PM 5 upon 90 DSI into G upon BSR, that comes 1.3128, and Kf ring E, that is Kf ring E1 equal to DSI upon DSI minus 2 bracket G plus 2 HR O plus HR minus GFB equal to 1.3128, and 5 PM equal to 5 is the average tau L stack in transformers, that comes 0.0660063 Weber, where tau equal to 5 DSI equal to B, and W1 5 PM KW 5 PM 261.7187 tons. So W1 is adjusted to an integer tons multiple of the product of poles and number of slot per pole. So W1 taken as equal to 260 tons. Now GD equal to 1 upon sin alpha PM by 2 upon G1 plus 1 minus sin alpha PM by 2 here, that comes 2.9281 millimeter, and GQ, that is 1 upon 1 minus cos alpha by 2 divided by G plus cos alpha by 2 divided by G1, that comes 1.7855 millimeter. And now comes from this LDM equal to 606 mu 0 and 1 K1 square tau L stack P pi square GD comes 0.1965 Henry, and LQM with the G6 mu 0 and 1 KW square divided by pi P pi square GD into tau into L stack, that comes 0.3223 Henry, and R bar equal to rho A1 L stack 1 HSR HPR, it comes 9.69 10 to the minus 5 ohm, and R ring equal to rho A1 to pi D ring upon NR A alpha ring B ring, that comes 3.7315 10 to the minus 6 ohm, and R equal to R bar plus R ring by divided by 2 sin square P pi upon NR, and it comes 1.8902 10 to the minus 4 ohm, and CW equal to HR O divided by BRO plus HSR upon 2 BSR divided by RB Y upon BSR plus HRO BRO0 plus HRO to BR0, that comes 0.2857. Now lambda SR equal to HRO upon BRO, that is in bracket 1 minus CW square plus HR upon T BSR in bracket 1 plus 3 CW into CW minus 1, putting value 0.6653, and lambda RZ equal to 2.5 G divided by 5 BRO plus 2G equal to 0.2254, lambda E ring equal to 3D ring divided by 2 NR L stack sin P pi upon NR into log bracket 4.7 D ring upon alpha ring plus 2 B ring, so it comes 0.8098, and LB equal to mu 0 L stack in bracket LSR plus LRZ ring, it comes 1.9232 10 to the minus 7 Henry, and K equal to NR upon 6 N1 KW, that's 0.0147, and RR equal to RB upon NR upon T 3 KI square, that comes 6.3788, or R equal to LB NR upon 3 KI square, that comes 0.0065 Henry. So now with these are the book and references from which this material is developed. You can have a look of this if you want, and thank you.